Do you feel like a coffee break? So do I. What about we talk more about the Gatherer API? This is definitely something you need to understand to work efficiently with streams, and it's not really a simple API. Last episode was already about gatherers, with a long introduction on the Stream API to understand how gatherers have been designed and why they have been designed like that. This time, I would like to focus only on gatherers, with more examples and more patterns that you can't implement with the Stream API. You will hear about integrators, downstreams, mutable states, stream interruption, finishers, parallel streams, gatherer chaining, and a little about the existing gatherer factories. If you need to check the Stream API again, you can watch the previous episode of this JEP Café. The link is in the description. Before we start, there are several things you need to know about gatherers. The first thing is that it models an intermediate operation on the Stream API, that is an operation that returns another stream. So you can see a gatherer as some kind of equivalent of a collector, but for intermediate operation. And this has two consequences. First, a gatherer gets its data from another stream that I'm going to call the upstream. And this upstream could be a stream opened on a collection or any other source, or it could be the result of a mapping, a filtering, any kind of other intermediate stream operation that could also, by the way, be a gatherer. Remember that each intermediate operation of the Stream API creates a new stream object. So a stream itself can be the source of another stream. And the second consequence is that a gatherer pushes its result to another stream that I'm going to call the downstream. And the same goes for the downstream. It could be another intermediate stream operation, or a reduction, or a collection, that is a reduction in a mutable container. And the second thing is that it allows you to implement operations that you cannot implement in a Stream API in its current state. Even if you're an advanced Stream user and you know how to write your own splitters, there are still things that you cannot do with the splitter API and that you can do with the Gatherer API. At this point, we can already state the first principle of the Gatherer API: only use them when you really need them. Writing a gatherer is not simple. The code you will be writing is not that easy to understand, so using a gatherer where you could use a simple pattern is probably not a great idea. And this can make the learning of the Gatherer API a little frustrating, because you need to go through a series of steps that you are not going to use in your application. The first example you will see in a minute is a mapping, but the map method is so much simpler that the mapping gatherer is not something that you will be using. And this is what you are going to see in this JEP Café, a series of boring examples, way too simple to be relevant in an application, that consist in implementing classical intermediate operations of the Stream API with gatherers. But this is what you need to understand how this API is working and how you can implement complex and useful patterns with it. So first thing first, let us write a simple, boring mapper with the Gatherer API. And even before doing that, just a few words on the technical aspects of the Gatherer API. This API is made of 3 elements that you can use as entry points, plus some others. The first one is the Gatherer interface. It is defined on 3 types: the types of the elements it consumes, the type of the elements it produces, and a third type, which is the type of the internal mutable state a gatherer can have. We'll leave this one for the moment, more on it in a minute. The second one is a gather method on the stream interface. This method takes a gatherer as a parameter and returns a stream of the type returned by this gatherer. And the third one is the gatherer's factory class. There are several factory methods in it that you can use to create pre-made gatherers. Again, more on that later. And there are also other interfaces and factory methods that you're going to see in a minute. Now, let us map a stream with a gatherer. And again, just a word of warning, modeling a mapping with a gatherer is a stupid idea. It is just useless to do that because you'll end up with a complex code, way more complex than calling a simple map method. But on the other hand, it's also easier to start with simple examples. So, suppose that you have this stream, which is a simple stream of strings of characters, and what you need is to map it to integers, mapping each string to its length. The code without gatherers is super simple. It's this one, and you can even write it with a method reference that can make it even simpler and even more readable. How can you write it with a gatherer? Well, for that, you first need to write a gatherer, and there are several ways of writing a gatherer. From a technical point of view, a gatherer is an interface that is functional, so you can implement it with a lambda. But this is not how we are going to create this mapping. This lambda is a supplier of another lambda expression, so the syntax would be this one, which is probably not the most readable code you've ever written. The second way to create a gatherer is to use the off factory method on the gatherer interface. This factory method defines two types, one for the elements of your upstream and another one for the elements of your downstream. This method takes an integrator as a parameter, which is another interface defined by the gatherer API. An integrator just models the integration of an element to a downstream. The integrator interface is defined on the same input type and return type as the gatherer. And it also defines another type, second in the definition, and we'll talk more about it later. In a nutshell, it's the internal mutable state your gatherer can define. So let us put it to void for now and ignore it. You can implement this integrator with a lambda. Now, the role of this integrator is the following. It is called by the stream implementation for each element produced by the upstream. And the role of this integrator is to push something to the downstream. That something usually depends on the element received and maybe some internal mutable state. So this lambda takes three parameters, but you're going to ignore the first one for now. It's actually the internal mutable state of this integrator. Again, more on that in a minute. The second element is the element coming from the upstream. And the third models the downstream. The type of this third element is downstream, which is an interface that models precisely the downstream. But this interface is not related to the stream interface itself. The most basic implementation you could write just consists in returning true, because this lambda returns a boolean and you need to return a boolean to make your compiler happy. In that case where you return true and don't touch this downstream object, your downstream will be empty because you haven't pushed anything to it. If you want to push an element to the downstream, all you need to do is to call downstream.push and pass this element. And if you want to map this element from the upstream, well, you just need to apply this mapping and push the result. Note that the downstream.push method returns itself a boolean that you can just return. Written in that way, this code works, but there is still something that is not quite right, so more on that in a minute. So you can use this mapping gatherer to process your stream in that way, and it just works as expected. You can probably imagine how you can write a filter operation with a gatherer. It's pretty easy. All you need to do is to decide if you want to push the element you get from the upstream to the downstream or not. So you can write it in that way. If your string of character is longer than 3, then you push it. But note that you still need to return a boolean. And since in the else branch you're not calling downstream.push for this element, now you need to return your own boolean. You cannot rely on what the downstream told you. So just a rule of thumb, when you don't know what to return in an integrator, and it's the case here, you can just return true. This is the default value you need to think about. It may not be optimal, but it cannot be wrong. Returning false may be wrong, so only do that when you know what you're doing. So let us return true for now. It makes the compiler happy, which is what we need. And we'll talk more about what to return exactly in a minute. This nice thing with gatherers is that you can fuse a mapping and a filtering in the same gatherer. I'm not sure that this will make your code more readable, but this is still something you can do. Neat. Of course, the next operation you may have in mind is the flat mapping operation. And indeed, there is no restriction on how many times you can call downstream.push. For instance, this function creates a stream of letters from a string of characters. If you run it, this is what it prints. But here you see that you have at least one problem. You are pushing all the elements that your function is producing without ever checking the boolean returned by this call to downstream.push. And you just return true at the end. As I told you earlier, this is okay, it will work, but it is suboptimal. Checking the result of downstream.push for every call would be better. So maybe this is the right time to see what does this boolean returned by downstream.push really mean, and see how you can improve this code. And by the way, this problem is not the only one that this code has. Writing a flat map in this way actually contains several bugs that we are going to fix. To understand what is wrong with this previous code, you first need to understand what is this downstream object and how you should be using it. First, downstream is an interface that is pretty simple. It has only two methods, and one of them is a default method, so you can implement your own downstream with a lambda if you wish to do so. The first method is push, and calling this method with an object will push this object to the downstream. Easy enough. And the second method is rejecting. It gives you access to the internal state of this downstream object. By default, a downstream is always non-rejecting. What does it mean for a downstream to be rejecting? It means that if you push an element to it, this element will not be taken into account. It means that the downstream will not do anything with it. Think of a limit 5 call, for instance. If you're pushing a sixth element to it, this element will just be thrown away. Note that if you push an element to a rejecting downstream, nothing will happen. You will not get an exception or anything like that. You're just doing something that is useless, so your code is suboptimal. How is this internal mutable state working? Well, there are three things that you need to know about this rejecting state. First, when you get a new downstream object, it is always non-rejecting, so you can always push something to it. You may be thinking, yes, but in the case where your downstream is equal to limit 0, then shouldn't my downstream be rejecting upfront? Well, actually, in that case, the stream implementation is smart enough not to call your gatherer at all. So no problem there. Second, once rejecting becomes true, it cannot become false again. So once a downstream becomes rejecting, it's done. It will not suddenly accept more elements after a while. So you can do the cleanup you need to do and close your stream. And third, and this is true for all the implementation you get from the JDK, this rejecting state can only commute on a call to push. It cannot commute on its own. Now, the fact is, you can, if you need, create your own downstream implementation that could commute on its own, like on an external clock, for instance. Now, you may be thinking that before pushing to a downstream, it may be an optimization to check for this rejecting state with a piece of code that could look like this one. So let us analyze this code for a minute. The question is, when is this code going to make your integrator exit before pushing an element? So when is this line of code going to be executed? As you know, when it is first called, a downstream is always non-rejecting. That's the rule number one. So when this integrator is first called, it is not. Then, as you also know, the rejecting state can only switch on a downstream.push. So, first case, this push call returns true, then the element is pushed, the downstream is non-rejecting, and the processing continues. The integrator will then be called with the next element if there's one, and your code checks again to see if the downstream is now rejecting. But as you also know, this rejecting state can only change on a call to push. And last time you called push, it was false. And it could not change in the meantime. So it is still false, and again, this code is not called. The second case is that downstream.push returned false, and in that case, your integrator also returned false. And because you did that, your integrator will not be called again. What you said is that I'm done accepting elements, so don't call me again. So actually, if you return the boolean you get from downstream.push correctly, then this code is never called and does not trigger any possible optimization. If you didn't create any downstream implementation that can commute this rejecting state on its own, like on a clock, for instance, then adding this code to an integrator is useless. It's not an optimization. Don't do it. And then you may be wondering, why can you check for this state at all? And you'll see that in a minute. So now you know how you can use a downstream object. There is just one last point that you need to keep in mind. This rejecting state is an internal mutable state of the downstream object. And I don't know for you, but personally, when I hear that little music, the first question that comes to my mind is it thread safe? When you have a mutable state, asking yourself this question should be a reflex. Mutable states usually don't play well with multiple threads. And indeed, this rejecting state is not thread safe. The implementations of downstream you can get from the JDK are not thread safe. And you may be thinking, why bother? This is called in a lambda, called by a stream. There is only one thread in that context, right? Well, not quite. Streams can be parallel, right? And in that case, your lambdas will be called by different threads. So let us pause this point for now. We will come back to it in a minute. Let us go back to our flat map operation and suppose now that you want to create a factory method that just takes the flat mapping function and that returns a flat mapping gatherer. This method could look like this one. Note that you can probably need to add some super E and extends R in the generic declarations, but we'll leave that aside for now. So you need to apply this method to each of the elements you get and push every element generated. And this is the code we wrote earlier to do that. And you know that this code is not the right one, because you need to check if the downstream becomes rejecting for every element you push. So you want to push elements to the downstream until the downstream becomes rejecting. If you state your problems with these words, then the code you need becomes simple. You can just use the take while from the stream API, and if the predicate is true, then push to the downstream. That code would look like something like that. This version is better because it will stop pushing as soon as the downstream becomes rejecting. But if you want to be picky, you could say that it is still suboptimal as you first check the rejecting state of the downstream before pushing to it. And you know that the first check is true, so you shouldn't be doing it. You don't need to do it. You can actually fix that by calling another method, which is allMatch. allMatch takes a predicate, and as soon as this predicate resolves to false, then allMatch interrupts the stream and returns false immediately. So in that case, you push, check the state, and decide if you should carry on and directly return the result of this allMatch call. So this is probably the most efficient way of writing this flat mapper. This pattern is very interesting, and you can use it every time you need to push a series of elements from an integrator. But it may be not as readable as the previous one. That being said, there are still annoying bugs in this code that I'm going to show you. The first bug is the following. It comes from the fact that you have no information on the stream that is produced by the function you get as an argument. This stream could be any stream opened on any resource. You need to keep in mind that a stream can be opened on many resources, and that some of them are I/O resources, like files, that need to be closed. This is the case for files.lines, for instance, that streams the lines of a text file. If you do not close your stream, then the underlying resource is not closed neither, leading to some resource leaking that in the end could kill your application in the long run. So you need to be careful with that. Fortunately, there is a very simple solution to that leverages the fact that the stream interface extends auto-closable. So all you need to do is to open your stream in a trial with resources statement, and you're done. The close method of the stream will be called, and if this stream has been opened on an I/O resource, this resource will be closed properly. Simple enough. Unfortunately, there is still a sneaky bug that is there, and that could make this code fail. Remember that we talked about this rejecting internal mutable state in the downstream object, right? And that this state is not protected against race condition. You may be wondering, yes, but what does it have to do with this code? Well, it has to do that once again, you don't have any information on the stream produced by this flat mapper. And it could be parallel. And if it is, then you're doomed, because this downstream.push will be called by different threads, meaning that you would have a good old race condition there. How can you protect yourself against that? Well, I'm sure you know that there is a parallel method on the stream API that you can use to make your stream parallel. And it turns out that you also have a sequential method that can turn a parallel stream to a sequential one. And this is what you want to call to protect your code in that case. Now, if you really want to protect yourself against anything, you should also check if this flat mapper can produce null instead of a stream. What could you do in that case? Well, I think you have two solutions. Either it's a bug and then you can fail with a null pointer exception and some meaningful error message, or it just means that there is nothing to produce there and then you can ignore it and wait for the next element. Or maybe there is some other solution. I would say it's really up to you and your application to do that. How you want to handle this null value really depends on what you want to do. But at least now you're protected against that. At this point, you saw how a gatherer can receive elements from an upstream and how it can push something to a downstream, taking into account the rejecting state of the downstream to continue or to stop pushing. Let us go through an example, which is the skip example. Skip takes a long as a parameter and skips the corresponding number of elements from the upstream. So what you need is a counter that you can increment for each element that you get from the upstream, and once this counter reaches the threshold, then you can start pushing. Don't remember to return true before starting to push, because if you don't, you are going to interrupt your stream. Let us begin by writing this code that implements this simple behavior. Of course, written in that way, this code cannot work for several reasons. The main one being, mutating a counter in your integrator in that way would not keep this mutation from one element to the other. That is, from one call of this integrator to the other. So for that, you need a wrapper. Let me create this box class, and the instance you get needs to be always the same from one call of your integrator to the other. But because this box instance has a mutable content, you will be able to update it. So the code will look like something like that. Now, the gatherer implementation needs a way to create an instance of this box class. And for that, you need to give a supplier to the API. Now, for some reason that you will see in a minute, this gatherer cannot be used in parallel. So instead of calling the off factory method, you need to call off sequential and pass these two arguments. Written in that way, this gatherer works correctly and does what it should be doing. How is it working? Well, before calling your integrator for the first time, the implementation first calls your supplier once and only once to create a single instance of this mutable state. Then this instance will be passed to your integrator for each element of the upstream until there is no more or until your integrator returns false. By the way, you can also use an anonymous class to create such an object and leverage the fact that the compiler will create a non-denotable type for it in that way. I like that because in this way, everything is contained within the definition of your gatherer. It probably makes anonymous classes great again, since it can make your code simpler without hurting its readability. By the way, creating a limit gatherer is almost the same. All you need to do is to push the elements until you reach the limit, and when you do, return false. This will interrupt the stream and your integrator will not be called anymore. Let us move on to a more complex gatherer, which is the distinct gatherer. A distinct gatherer would need an internal mutable state that could be a HashSet. You can add the elements you get to this HashSet. If it's already in it, then you don't push it, and if not, then you can push it. Don't forget that when you don't push anything, you still need to return true, because your downstream is bound to be non-rejecting and you can still push more elements to it. Returning false would interrupt the stream, and this is not what you want to do. As you can see, dealing with this internal mutable state is actually very simple and very logical, and you can do many things with it. The distinct gatherer and the limit gatherer have one thing in common: they do not push all the elements they get from the downstream. But they also have something that is fundamentally different. The distinct gatherer does not interrupt the stream by itself. Its integrator never returns false by itself, whereas the limit gatherer does. At some point, its integrator decides on its own to return false and to interrupt the stream. An integrator that does not interrupt the stream on its own is called the greedy integrator. And you can tell the API that your integrator is greedy by passing it to the off-greedy factory method of the integrator interface. The writing of your integrator is the same, there is no difference to it. A gatherer built on a greedy integrator will always take as many elements from the upstream as it can, and may decide to push some of them, all of them, or even none of them. What difference does it make? Well, the Stream API implementation can use this information to optimize things internally and give you better performance. Don't worry if you create a greedy integrator, but forget to call the off-greedy factory method, nothing bad will happen. Your code will just work fine. So you can write the previous distinct gatherer in that way with this call to integrator.offGreedy. Once again, if you forget about it, I would say it's a missed opportunity, but nothing bad will happen to your stream. We are not done with the elements you can use to create gatherers. There are still two more to go through that you need to see. And the next one is called the finisher. Let us take another example and build the sorting gatherer. You can do that from the distinct gatherer by just replacing this HashSet with a TreeSet, which technically makes it a sorting and distinct gatherer, but never mind. The integrator of the gatherer cannot push any element to the downstream because the first element it needs to push is the smallest element of your stream. And to tell which element it is, you need to see all of them. So all you can do in your integrator is add the elements to the sorted set and return true without pushing anything. And by the way, this makes it a greedy integrator. But then, when are you going to push the elements that you have in your sorted set? Your integrator is not called anymore when there are no more elements produced by the upstream. So how can you push these elements to the downstream? Well, this is precisely the role of this finisher object. You can see a finisher as a degraded version of an integrator. A finisher takes the same parameter as the integrator does. The only thing is that there is no more element to push to it, so it does not take any element. And since this is the last element of your gatherer to be called by the implementation, after it there is nothing left. It does not need to return anything. A finisher is only called once, and that's it. So a finisher actually needs two parameters to work: the state, because this is where your precious objects are, and the downstream, because this is where you need to push them, and it does not return anything. A finisher has the structure of a big consumer of state and downstream. So now you can write this finisher, just take all the elements of your internal state and push them one by one in a whole match that will check the rejecting state of your downstream every time you push something to it. As you can see, this pattern creates a stream on your TreeSet and tries to push a first element to the downstream. Could it be that this downstream is rejecting at this point? Well, when you were in an integrator, you had the guarantee to get a fresh downstream that was never called before. So the rejecting state was false, because this is how downstreams are working. But now you are in a finisher, and this downstream may have received objects before in your integrator, and it may be already in a rejecting state. So does it make sense to check for this state before doing anything? Well, the answer is yes, or at least maybe. Because the real question is, does it make sense for your application to check if the downstream is rejecting? And this is really up to you to decide in the context of your application. And you see that the situation is not that simple. In the case of the sorting gatherer, we never called downstream.push, so we know that this downstream is not rejecting. But generally speaking, it could be rejecting. Is the pushing of the first element an overhead that you absolutely want to avoid? If the answer to this question is yes, then you should check this state. If it is no, then don't bother. Checking for this rejecting state can make sense in a context of a finisher, and you should ask yourselves this question. In the context of an integrator, it does not. Never. One of the amazing features of the Stream API is that you can very easily go parallel by just calling parallel on an existing stream. The Gather API supports parallel streams in its own way by adding something that the Stream API doesn't have and cannot do. What does it mean to be executed in parallel for a gatherer? Well, there are two cases, an easy one and a less easy one. And you already saw them, by the way. The first easy case is when you have a gatherer that does not define an internal mutable state, and you created these gatherers with the gatherer.off factory method. These gatherers can be used in parallel without any problem. The second, less easy case is when your gatherer needs to define an internal mutable state. And in this case, you use the gatherer.off sequential factory method to create it. As its name may suggest, this gatherer does not support parallel computations. But what does it mean? It does not support parallel computation. Well, it means that this gatherer cannot be executed by different threads at the same time. But it does not mean that you cannot use this gatherer in a parallel streams. Actually, you can, and still get better performance. The only thing is that this gatherer will always be executed in a single thread. Let me show you an example of that. Let us create a parallel stream that is processing 1,000,000 integers. And let us map these indexes to the thread name that is executing this mapping function. And by the way, let me call distinct because we only need to know the different threads being used. And now let us add a gather call with a sequential gatherer. This gatherer is just pushing the thread name to the downstream, but it also adds the thread name that is executing in an external set. And then after this gatherer, let us add the same kind of code in a pick call to see what threads are executing the rest of the stream processing. A word of warning with the pick method. This method has been added for debugging purposes. It is not meant to be used in a production code, and certainly not to conduct side effects as we are doing it here. So don't take this code for an example of what you can do in your application. It is made to show you how things are working, and that's it. That being said, in the end, you have three collections. The first one, called threads upstream, contains the name of the threads that were used to execute the upstream of your gatherer. The second one, called threads gatherer, is for the thread names that execute your gatherer. And the third one contains the thread names that were used for your gatherer downstream. And if you print the number of elements of each collection, you will get a result that looks like this one. It means two things. First, I probably have 16 CPU cores on my machine. And second, yes, you can use a sequential gatherer in a parallel stream and still get better performance because your upstream and your downstream are indeed executed in parallel. By the way, you can make this gatherer parallel by just replacing this off sequential call with a off call and run this code again and see that now you have a classical parallel stream. Why can't you create parallel gatherers that have an internal mutable state? That is a gatherer that is declared with only a supplier. Well, actually you can, but you need to give one more element to the gather API. What is happening is the following. The stream API needs to run your gatherer. So first, it creates an instance of your mutable container using the supplier you provide. The rule is each thread has its own instance of this container, meaning that it does not have to be thread safe, which makes things simpler for you. But on the other hand, it can only create one such instance, because if it creates more than one, then the stream API will need to combine them when your integrator is done integrating. So if you want to create a gatherer with an internal mutable state and you want to support parallelism, you need to provide another element called a combiner that is able to combine two instances of this mutable state together. This combiner takes two instances of your mutable container and returns one. It is a binary operator of your mutable container. If you can provide such a combiner, then you can create a parallel gatherer with an internal mutable state. Let us write again the distinct gatherer that you wrote previously, but this time in a parallel way. First, you need to provide an initializer for your internal mutable state that does not need to be thread safe, so plain HashSet will do. And then you need to provide your integrator. But this time it's too early to push anything to your downstream, because you don't know if some other thread has seen the element this integrator is looking at. So all you can do is add it to your set without pushing it. And then when all your threads are done adding elements to these sets, you need to combine them, which is a simple add-all. And when the stream API is done calling your combiners, it will end up with a single set with all the distinct elements of your upstream. So now you also need a finisher. It was not the case in the non-parallel version, and this finisher pushes all the elements of your set to the downstream, checking if this downstream is rejecting or not. So you see that creating a parallel gatherer is a little more complicated than a sequential gatherer. You need to write your algorithm taking into account that you are only processing a portion of the elements your upstream is pushing to you. And then you need to also provide a combiner and most of the time a finisher. This added complexity is the price to pay to create parallel gatherers. Is it worth it? Well, this is something you need to check. When it comes to performance, as always, measure, don't guess. The Gather API allows you to chain your gatherers, which is really nice. All you need to do is to call the andThen method on your gatherer and pass another gatherer as a parameter. Of course, the types must be compatible. The return type of the first gatherer needs to match the input type of the second one, which is only expected. And if you check the implementation of the resulting gatherer, you will see that a lot of work has been put in it to create an optimized gatherer. Internally, there is a gatherer.composite class that models this composed gatherer and you can check this class for its implementation. Then you may be wondering, is it better to chain gatherers with this andThen method, or to fuse the code of several gatherers into one, like a single gatherer that would do a mapping and a filtering? Well, chaining should be your first choice because of readability and because of all the optimizations that are used. But as usual, when it comes to performance, measure, don't guess. The last element I would like to talk to you about is this gatherers factory class that is part of the API. There is a number of factory methods in it. To create pre-made gatherers, you can definitely check the code of this class, as this can give you ideas about creating your own gatherer. It also uses some internal APIs of the JDK for performance reasons, so you can't just copy and paste the code as is, but you can still get some inspiration from this code. All the methods are doing some classical operations. There is one that is doing something quite unexpected from the Stream API, which is the mapConcurrent method. You know that the Stream API processes its element one by one from the source of your stream all the way to your terminal operation. And when you decide to go parallel, the same is happening. At the end of the day, your source is divided into small chunks of data, small enough to be processed sequentially in a single thread. Once this processing is done, the partial results are merged together into the global result of your operation. It means that whatever you do, mapping a stream is not about mapping all your elements and then moving on to the next operation. It is about mapping one element, then waiting for the result to be pushed to your final operation, and then mapping the next element. And there are use cases where this is not what you need. What you need is to apply your mapper to all your elements and get all the results and then move on. Well, this is exactly what mapConcurrent is doing. mapConcurrent creates a gatherer that consumes all the elements of its upstream and pushes the result to its downstream from within its finisher. So no element is pushed to its downstreams while there are still elements coming from the upstream. This gatherer is built on a mapper, which is a function, and an integer, which is the number of concurrent mappings that you want to support. Each element from the upstream is mapped using the function in its own virtual thread, and this is controlled by an internal semaphore. So the total number of active mapping is controlled by the concurrency levels you fixed. This gatherer gives you the possibility to have a parallel computation in a stream that is not itself parallel and in a controlled way, as you can limit the number of active threads at a given time. It does not use the fork join framework, and if you have concurrency issues, you need to manage them by yourself. As always, when it comes to concurrency, be careful because there are bugs that will never show up on your development machine and that you will have a very hard time fixing when you see them in production. In a nutshell, if you are not sure that you really need it, keep your stream simple and stay away from parallelism. And with this, I'm out of coffee, so that's it for today. Talk to you soon.